Hi everyone, my name is Hitha and today I'll be presenting our work on the naturalness of fuzzer-generated code. This project is a part of the NSF-RU program at Carnegie Mellon University. Fuzz testing is an effective method for automatic software testing, commonly used to find bugs in tools such as compilers, parsers, interpreters, web browsers, etc. Compiler fuzzers generate vast numbers of programs using randomized algorithms, oftentimes triggering real bugs in the software that processes such algorithms. In this project, we use the generation-based fuzzer Csmith. However, because of this random input generation process, the resulting bug-triggering programs are often difficult to interpret. In order to combat this problem, test input minimization techniques have been proposed to aid in the interpretability of fuzzer-generated programs by reducing the size of these inputs while still triggering the original bug. Researchers have discovered that human-written source code is surprisingly predictable to language models designed to capture recognition in natural languages. As a result, this high predictability of code is often referred to as naturalness. Language models have also demonstrated that buggy code is relatively less predictable than correct code, and that predictability tends to correlate with readability. We use entropy as a proxy for predictability in this work. Our principal research questions are fuzzers effective at triggering bugs because their inputs are highly unpredictable? And does reducing such bug triggering programs yield more predictable and thus perhaps more readable programs? We find that these programs are rather predictable, but this doesn't necessarily mean that they're natural. Additionally, reducing these programs did not improve the code predictability in a consistent or substantial manner. We trained a standard size transformer model on human-written code on a corpus of C programs from GitHub. We also collected 98 compiler bug triggering programs generated by Csmith, along with their corresponding minimized programs by CReduce. We used entropy as our principal metric for analysis in this work. Our primary result concerns the relative predictability of fuzzer-generated programs given a language model trained on human code. We find that surprisingly, the developer-written code are the least predictable here. Additionally, the automatically generated C test cases are more statistically predictable than human-written code, having a lower entropy than the former. This surprising result is likely because of the high degree of repetition present in Csmith code. We also find that buggy programs, originally thought to be more entropic, had a lower entropy value and thus were deemed more predictable than Csmith-generated programs. We then decided to train a language model that learns the distribution of fuzzer-generated code. This model finds developer-written code far more surprising than vice versa. We also find that the original unreduced bug-triggering programs are nearly twice as entropic as the randomly generated programs. This suggests that such programs are still relatively rare and complex compared to randomly sampling valid programs. We also see that entropy does not necessarily decrease monotonically throughout the minimization process, as seen in these figures that plot the entropy during this process for 4 buggy programs. Overall, we found no consistent trend. While CReduce tends to reduce the average entropy, individual reduction steps rarely have a consistent effect either way, and entropy mostly changes in large jumps when a significant chunk of code is removed. Our findings inform our vision of guiding fuzzers directly with entropy and highlights the need for similar investigations of other types of fuzzers, as well as test case minimization tools. Thank you for your time.